Today's topic is section 5.3. It's called the net change theorem and average value. At this point, we've seen definite integrals. The notation is the integral from a to b of f of x dx. Okay, these were introduced in section 5.1. In section 5.2, we talked about the fundamental theorem of calculus, abbreviated FTC, and that was written: the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where the understanding here is that capital F is any antiderivative of the integrand lowercase f. We thought about the fundamental theorem as a shortcut for evaluating definite integrals. All right, we've talked about some reasons for why we want to compute definite integrals, going all the way back to computing total cost given marginal cost. Being an antiderivative, capital F being an antiderivative of lowercase f, that means that capital F prime is equal to lowercase f. In other words, the derivative of the antiderivative is the function itself. With that in mind, we can rewrite the fundamental theorem of calculus, part 2, and what we end up with is what this section is calling the net change theorem. And it looks like this: the integral from a to b of lowercase f, but remember lowercase f is actually capital F prime, so in place of lowercase f, I'm going to put capital F prime as my integrand. And what that turns out to equal is capital F of b minus capital F of a. Now, way back in the beginning of the semester, we interpreted a derivative as a rate of change. And so over on the left-hand side of this equation, I'm trying to integrate a rate of change over the interval from a to b. And it turns out that when I do that, from the fundamental theorem, I get this difference. But we know that a difference is a way to measure change. And so in particular on the right-hand side, instead of a rate of change, we now have a net change in the original function, capital F, over the interval from a to b. Right, we plug in the value of capital F at the end point b, at the final point b, and then subtract where it was initially. In other words, at lowercase a. So in this section, they give a bunch of different applications of this idea. Right? In this course, we've thought about many different applications where rates occur: velocity, marginal cost, marginal revenue, marginal profit, and the list goes on and on and on. Okay? Let's do a few examples. This first example is 5.3, number 11. We're told here that the marginal cost of manufacturing Y yards of a certain fabric is given by this quadratic function, C prime of Y. Right? C prime, we know that that's marginal cost. The units for marginal cost, like we're used to, are dollars per yard. And then I'm supposed to try to figure out how much the cost increases. Find the increase in cost, actual cost, if the production level is raised from 2,000 yards to 4,000 yards. So what we're asked to find here is the difference between the cost of producing 4,000 yards and the cost of producing 2,000 yards. The problem is I don't know what the cost is. Right? But what I do know is the marginal cost. So because this is what I want, right, this is the change in cost from going from 2,000 to 4,000 yards of production. But this is a difference, right? I'm thinking about this as f of b minus capital F of a. Right? And so if I use the net change theorem, what this tells me is that this difference is really an integral. It's an integral of the derivative of c, so c prime of y. We're integrating with respect to y. And what are the a and the b in this case? Well, the a is 2,000, so that's my lower limit of integration, and the b is 4,000. That's the upper limit of integration. Fortunately, in this example, I am given the marginal cost. So I can replace c prime of y with the formula that they gave me. So here I'm computing an integral from 2,000 to 4,000 of 3 minus 0.01y plus 0.000006 y squared dy. Okay, using the fundamental theorem of calculus now, we know how to integrate this. The integral of 3 is 3y, and then we do minus 0.01. It's a constant coefficient, so it stays there. The integral of y is y squared over 2, and then plus 0.5 zeros and then a 6, and then the integral of y squared is y cubed over 3. Right, so here's my antiderivative. This gets evaluated from 2,000 to 4,000. Like we're used to, we have to plug 4,000 in for y first, and then subtract and plug in 2,000 for y. You can check that, and the answer that you should get is 58,000, I believe. Yes, $58,000. All right, so that's the increase in the cost when production is changed from 2,000 to 4,000 yards. Right here is the net change theorem. The other topic in this section is average value. I'm not going to say too much about this, but you should read about it in the book. The definition for average value is something like this. The average value of a continuous function y equals f of x over the interval AB is, let's call it f sub avg for average. You do an integral of the function over the interval from a to b, and then you divide by the length of that interval. All right, computing this quantity will give you an average value for the function over the interval AB. Number 35 asks us to do an average value computation. We're told that the concentration of a drug in a patient's bloodstream measured in milligrams per liter t minutes after being injected is given by this formula C of t. So not cost, but concentration this time. It's 8 times the quantity, e to the minus 0.05 t minus e to the minus 0.4 t. We're supposed to find the average concentration of the drug in the bloodstream during the first 20 minutes. If you think about the medical profession, right, you certainly need to know how much of a particular drug is in a patient's body at some time, or at least you want to have a sense of how much it is, how much is there. So, since it's asking us about average concentration, right, let's call the answer C sub AVG for the average concentration. And just like the definition tells me, I have to compute the integral of the function, the definite integral of the function, of the original function, so 8 times e to the minus 0.05 t minus e to the minus 0.4 t with respect to t. I'm looking for the average over the first 20 minutes, so I'm going to say t goes from 0 to 20, right? That would be the first 20 minutes. So my interval here, my time interval is 0 to 20. I don't want just the integral of the concentration, but I have to divide by the length of the interval. So I have to have a 1 over 20 minus 0 in front of the integral. All right, if we work this out, this is 1 over 20. The 8 is a coefficient, and so that can be factored out. We've seen in a previous section that when we integrate e to the kt with respect to t, we end up dividing by that constant coefficient, so we get 1 over k e to the kt. Here's what it looks like. I get 1 over minus 0.05 e to the minus 0.05 t. Okay, the k in this example is minus 0.005. And then I have a negative from the subtraction. When I integrate e to the minus 0.4 t, I have to do the same kind of integration. The k here, though, is minus 0.4. So I get 1 over minus 0.4 e to the minus 0.4 t. That's the integral, but it now has to be evaluated from 0 to 20 because we're applying the fundamental theorem of calculus. Like we've seen, plug in the 20 for t first, and then subtract and plug in the 0. Once you do that, the answer turns out to be approximately 4.06. And the units here, right? In the integral, I multiplied by units of time, but I'm also dividing by units of time. So the time unit cancels out, and all that I'm left with are the units for the integrand, but the integrand is just my concentration. We were told that the concentration had units of milligrams per liter, and so my answer also has units of milligrams per liter.